Welcome to this episode of Mentors at Your Benchside, the podcast giving you advice, tips, and tools for getting the most out of your research. I'm Laura Grassi, and today I'll be talking to you about how STS Page works. But first of all, why should you care? Understanding how techniques work allows you to tweak and adjust for optimal results, but also troubleshoot when things go wrong. So let's get started. STS Page, or sodium dodecyl sulfate polyacrylamide gel electrophoresis, is commonly used in the lab for a separation of proteins based on their molecular weight. It's one of those techniques that's commonly used but not frequently properly understood. So let's try and fix that by explaining just how STS Page works. The first thing to know about how STS Page works is that it separates proteins according to their molecular weight, based on the differential rates of migration through a sieving matrix, the gel, under the influence of applied electric field. The movement of any charged species through an electric field is determined by its net charge, its molecular radius, and the magnitude of the applied field. But the problem with natively folded proteins is that neither their net charge nor their molecular radius is molecular weight dependent. Instead, their net charge is determined by amino acid composition, that is, the sum of positive and negative amino acids in the protein, and molecular radius by the protein's tertiary structure. So, in their native state, different proteins with the same molecular weight would migrate at different speeds in an electrical field, depending on their charge and their 3D shape. To separate proteins in an electrical field based on their molecular weight only, we need to destroy the tertiary structure by reducing the protein to a linear molecule and somehow mask the intrinsic net charge of the protein. That's where STS comes in. STS is a detergent that is present in the STS Page sample buffer where, along with a bit of boiling and a reducing agent, normally DTT or beta-mercaptoethanol, to break down protein-protein sulfide bonds. It disrupts the tertiary structure of proteins. This brings the folded proteins down to linear molecules. STS also coats the protein with a uniform negative charge, which masks the intrinsic charges on the R groups. STS binds fairly uniformly to the linear proteins at around 1.4 grams of STS per 1 gram of protein, meaning that the charge of the protein is now approximately proportional to its molecular weight. STS is also present in the gel to make sure that once the proteins are linearized and their charge is masked, they stay that way throughout the run. The dominant factor in determining an STS-coated protein's mobility is its molecular radius. STS-coated proteins have been shown to be linear molecules, about 18 angstroms wide and with length proportional to their molecular weight. So the molecular radius, and hence their mobility in the gel, is determined by the molecular weight of the protein. Since the STS-coated proteins have the same charge to mass ratio, there will be no differential migration based on charge. In an applied electrical field, the STS-treated proteins will now move towards the positive anode at different rates depending on their molecular weight. These different mobilities will be exaggerated due to the high friction environment of a gel matrix. As the name suggests, the gel matrix used for STS Page is polyacrylamide, which is a good choice because it is chemically inert and, crucially, can be easily made up at a variety of concentrations to produce different pore sizes, giving a variety of separating conditions that can be changed depending on your needs. On to the buffer system. To conduct the current from the cathode, negative, to the anode, positive, through the gel, a buffer is needed. Most use the discontinuous lamellae buffer system. Discontinuous simply means that the buffer in the gel and the tank are different. Typically, the system is set up with a stacking gel at pH 6.8, buffered by tris HCl, a running gel buffered by pH 8.8 by tris HCl, and an electrode buffer at pH 8.3. The stacking gel has a low concentration of acrylamide as we don't want the proteins to separate here, while the running gel has a higher concentration that is capable of retarding the movement of the proteins. So, what is with all these different pHs? Well, glycine can exist in 3 different charge states: positive, neutral, or negative, depending on the pH. Control of the charge state of the glycine by the different buffers is key to the whole stacking gel thing. So let's touch on how that works. When the power is turned on, the negatively charged glycine ions in the pH 8.3 electrode buffer are forced to enter the stacking gel, where the pH is now 6.8. In this environment, glycine switches predominantly to the zwitterionic neutrally charged state. This loss of charge causes the glycine ions to move very slowly in the electric field. The chloride ions from the tris HCl, on the other hand, move much more quickly in the electric field, and they form an ion front that migrates ahead of the glycine. The separation of chloride ions from the tris counter ion, which is now moving towards the anode, creates a narrow zone with a steep voltage gradient that pulls the glycine ions along behind it, resulting in two narrowly separated fronts of migrating ions. The highly mobile chloride ions at the front, followed by the slower, mostly neutral glycine front. All of the proteins in the gel sample have an electrophoretic mobility that is intermediate between the extreme of the mobility of the glycine and the chloride ions. So when the two fronts sweep through the sample well, the proteins are concentrated into the narrow zone between the chloride ion and glycine fronts. This procession carries on until it hits the running gel, where the pH switches to 8.8. At this pH, glycine molecules are mostly negatively charged and can migrate much faster than the proteins. So the glycine front accelerates past the proteins, leaving them in the dust. The result is that the proteins are dumped in a very narrow band at the interface of the stacking and running gels. And since the running gel has an increased acrylamide concentration, which slows the movement of proteins according to their size, the separation begins. If you are still wondering why the stacking gel is needed, think of what would happen if you didn't use one. The gel wells are around 1 centimetre deep, and you generally need to substantially fill them to get enough protein onto the gel. So in the absence of a stacking gel, your sample would sit on top of the running gel as a band up to 1 centimetre deep. Rather than being lined up together and hitting the running gel together, this would mean that the proteins in your sample would all enter the running gel at different times, resulting in a very smeared band. So the stacking gel ensures that all the proteins arrive at the running gel at the same time, so the proteins of the same molecular weight will migrate as nice tight bands. Once the proteins are in the running gel, they separate because higher molecular weight proteins move more slowly through the porous acrylamide gel than lower molecular weight proteins. The size of the pores in the gel can be altered depending on the size of the protein you want to separate, simply by changing the acrylamide concentration. These can be quite broad. For example, a 7% acrylamide gel can separate proteins with a molecular range between 50 and 500 kilodaltons. A 10% would be for 20 to 300 kilodalton proteins, a 12% between 10 and 200, and a 15% between 3 and 100 kilodalton proteins. For a broader separation range, or for proteins that are hard to separate, a gradient gel, which has layers of increasing acrylamide concentration, can be used. So I think that's about it for how STS Page works. Check out the episode description for links to related articles and resources. And don't forget to subscribe to the podcast to get more advice and help from mentors at your benchside.